In this illustration, we intend to simulate the ultimate consolidation settlement of NC clay layer using ChemClay plasticity in the Abaqus software. The soil is composed of two layers. The top layer is sand and the below layer is clay. You can also observe the consolidation settlement of soil in the right picture. Actually, we intend to simulate the example 4.3 of Sam Helwani book in the Abaqus software. Here you can observe geometric shape of soil that is 7 meters high. This question has been modeled in a two-dimensional plane strain form. Here, the ChemClay plasticity model has been used in order to define properties of the clay which can be observed. You can also observe the parameters of ChemClay plasticity model in this example. I'll enter the Abaqus software for simulation. I will click on Create Part. Here I intend to create the geometric shape of soil. I will make the modeling space as two-dimensional of deformable type. Shell, enter the rough size of the tracing page as 50 and continue. As you observe in the picture, the soil is composed of two layers, and the top layer is sand with a height of 6 meters, and the below layer is clay that is 1 meter high. The width of the soil has been considered equal to 0.2 meters. I will enter the height of the soil as 7 and its width as 0.2 meters. Done. In the next step, I'll select Partition from the Tools menu, then Face and Sketch, then draw a horizontal line and enter this distance equal to 6 meters and done. In this manner, the soil was divided into two partitions. In the next step, I'll enter Property module, click on Create Material. Here I intend to define the properties of clay. I'll select Density from General menu. The density is equal to 1923 kilogram per cubic meter. I will select Elasticity and Porous Elastic from Mechanical menu. Log bulk modulus that is displayed with kappa is equal to 0.01957 and the Poisson ratio is equal to 0.28. Then I'll select Plasticity and Clay Plasticity from Mechanical menu. Lambda is equal to 0.1174. Stress ratio is equal to 1. Initial yield surface size is equal to 26.85 kilopascal. Wet yield surface size and flow stress ratio is equal to 1. I will select pore fluid and permeability from Other menu, I'll enter specific weight of water equal to 9,810. The coefficient of permeability is equal to 6 multiplied by 10 to the power of negative 8 meter per second. As you observe in this diagram, the increase in the stress causes the void ratio to be changed. According to this diagram, the increase in stress causes the void ratio to be reduced as well, so that the void ratio would be changed from 0.8 to 0.69, and so I'll enter void ratio equal to 0.69 and OK. I will click on Create Material again. Here I intend to define the properties of sand. The properties of sand have not been referred to in Sam Helvany book, and so these properties were not mentioned in this example. So I will define the properties of the sand as I desire. I will select elasticity and elastic from mechanical menu. Young modulus is 100 multiplied by 10 to the power of 6 Pascal, and I'll enter the Poisson ratio as 0.3. Then select pore fluid and permeability from other menu. Enter specific weight of water equal to 9,810. The coefficient of permeability equal to 0.00016 meters per second, and void ratio equal to 0.8, and OK. I click on Create Section, select Solid and Homogeneous, then Continue. From here select Clay and OK. I will click on Create Section, Continue. Here select Sand and OK. I will click on Assign Section, select the top layer, done. Here select the sand and OK. Here I select the below layer, done. Select the clay and OK. The top layer is the sand and the below layer is clay. I'll enter Assembly Module, click on Create Instance and OK. I will click on Translate Instance, select the soil, done. First, I'll select this point and then the origin of coordinates and OK. I'll save the model. Enter Step Module, click on Create a Step. From here select Geostatic Step and continue. The definition of geostatic is aimed at making an equilibrium in the clay layer. Also, we will apply the effective weight of soil in this step. From here I'll select Automatic, enter Initial increment size equal to 0.1. From here select Unsymmetric and OK. I will click on Create. From here select Soils and continue. As it has been written here in the step 1, that is geostatic step, the effective weight of soil will be applied using the body force. In the step 2, a sudden compressive load with quantity of 100 kilopascal will be applied suddenly to the top surface of the soil. Time period is equal to 1 second. I'll enter maximum number of increments equal to 10,000. Initial increment size as 0.1. From here, enter maximum pore pressure change per increment equal to 1 multiplied by 10 to the power of 6 Pascal. Tick off this option. Here select unsymmetric and OK. I'll click on Create. As explained in the book, the consolidation process will be done in 6 sequent steps, and their time periods are 1, 10, 100, 1,000, 10,000, and 100,000 seconds, respectively. From here, I'll select Soils and continue. Time period is equal to 1 second. And here, I'll select Fix. As explained in Sam Helwani book, each step is divided into 10 sub-steps. So I will enter maximum number of increments equal to 10 and increment size as 0.1. Actually, time period is equal to maximum number of increments multiplied by increment size. From here, I'll select unsymmetric and OK. I'll click on Create. Select the soils, continue, enter time period equal to 10 seconds. From here, select Fix, enter maximum number of increments equal to 10 and increment size to 1 second. From here, select unsymmetric and OK. I'll click on Create again. From here, select Soils, continue. Time period is equal to 100 seconds. From here, select Fix, enter maximum number of increments equal to 10, enter increment size equal to 10 as well. From here, select unsymmetric and OK. I'll click on Create. Continue. Time period is equal to 1,000 seconds. From here, enter maximum number of increments equal to 10. Increment size equal to 100. From here, select unsymmetric and OK. I will click on Create again. Continue. Time period is equal to 10,000 seconds. From here, select Fix, enter maximum number of increments equal to 10, increment size equal to 1,000 seconds, and from here select unsymmetric and OK. I will click on Create. Continue. Time period is equal to 100,000 seconds. Enter maximum number of increments equal to 10, increment size equal to 10,000 seconds. From here, select unsymmetric and OK. Actually, the consolidation process is done in 6 consecutive steps. I will enter load module, click on create load. From here select geostatic step, then from here select body force and continue. I'll select the sand layer, done. Here we should enter the effective specific weight of sand. We will use this formula in order to calculate the effective specific weight, which is equal to 8,190 Newton divided by cubic meter, negative 8,190, and OK. I'll click on create load again, continue, select the clay layer, done. The specific weight of clay is equal to 9,190 Newton divided by cubic meter, negative 9,190, and OK. I click on create. From here select pressure loading step, then pressure and continue. I will select the top surface of the soil, done. In the step 2, a sudden pressure with a load and quantity of 100 kilopascal will be applied to the top surface of the soil. Well, from here we'll have 100 multiplied by 10 to the power of 3 Pascal, and here select amplitude instantaneous and OK in this manner. I will click on create boundary condition. From here select initial step, then displacement rotation and continue. I will select the bottom of the soil, done. Close the boundary conditions of U1 and U2 for it and OK. Then I will click on create boundary condition, hit continue. I'll select this surface, then this surface, done. Close the boundary condition of U1 for it and continue. I'll click on create boundary condition. From here select consolidation 1 step. From here select other and pore pressure and continue. I will select the top surface of the soil, then the below surface, then this surface, and done. Consider a pore pressure equal to 0 for them and OK. I'll click on create predefined field. From here select initial step, then select void ratio and continue. I'll select the whole of the soil, done. As explained in the book, the initial void ratio is 0.8. OK, I'll click on create predefined field. From here select geostatic stress, continue. I will select the sand layer, done. The height of soil in top surface is equal to 0, so the stress in this point is equal to 0. If we move negative 6 meters downwards, the stress will be calculated according to this formula. That is effective specific weight multiplied by the height. As explained in the book, the initial horizontal effective stress is assumed to be 50% of the vertical effective stress. Therefore, here I will enter the lateral coefficient as 0.5 and OK. The calculations of which can be observed here. I'll click on Create, select Geostatic, Continue, select the clay layer, Done. If we move 6 meters downwards in proportion to the original coordinates, the stress in this point will be equal to 49,140, negative 49,140. If we move 7 meters downwards in proportion to the original coordinates, the stress in this point will be equal to negative 49,140, negative 9,190. The lateral coefficient is equal to 0.5 and OK. I will enter Mesh module, click on Assign Element Type, select the soil, done. From here I'll put the element family on pore fluid stress. From here select quadratic, and as you observe, the name of the element has been distinguished here, CPE8RP. That's the name of the element, which can also calculate the pore water pressure. Well, I click on OK, click on Assign Mesh Control, select the soil, done. From here select Structured and Quad, and OK. I'll click on Seed Edge, select these lines, done. As explained in Sam Helvani book, one element would be considered directed at x-axis, and OK. Then I will select these two lines, done. This is while 6 elements have already been considered for the layer of clay. Here I will select the two lines, done. Consider the number of 50 elements for them, and OK. I'll click on Mesh Part, and yes, and meshing is made in such manner. I will enter Job module, click on Create Job, Continue, click on Submit. The analysis was done successfully, so I'll click on Result. The simulation is actually aimed at developing such a diagram. In fact, we intend to draw the diagram in the Abaqus software and compare the results obtained from the Abaqus software with those gathered from Sam Helwani book. I'll click on Create XY Data. From here select ODB Field Output and continue. From here I'll select Unique Nodal. From here U2, click on Edit Selection and select this node, Done, and Plot. I'll double-click on the horizontal axis and from here select a logarithm so that the diagram can be drawn logarithmically in this manner. From here I'll right-click, Edit, select the first column, copy, and paste that in the Excel software. As you can observe here, the unit of time here is hour. Therefore, we should convert second to hour. So I'll select this column and divide all the quantities in it into 3,600 seconds. After that, I will select this column, copy, and paste that here. I'll select these two columns, click on this diagram from the Insert menu, from here tick on Logarithmic Scale option in this manner. From here I'll click on File and enter this diagram into the Excel software in this manner. The diagram having been marked in blue color is one obtained from the Abaqus software, the results of which is quite concordant with those obtained from some Helvani book. Here the ultimate consolidation settlement quantity is equal to 0.0627 meters. That actually equals the same 62 millimeter, and as it is observed here, the resulted consolidation settlement is almost 62 millimeter, and with regard to the results obtained from the Abaqus software before, we will infer that the consolidation settlement is 62 millimeter.